notes for AP Calculus on the topic of position, velocity, and acceleration. So remember, velocity is defined as the rate of change of position. And remember, rate or rate of change is just another word for the derivative. So the velocity tells you how the position is changing over time. And acceleration is the rate of change of velocity, or derivative of velocity. With respect to time. So it's telling you, your acceleration tells you how the velocity is changing over time. So if we start with our position function, which is called all kinds of things, including s of t, then to go to velocity, you can write it as v of t, or s prime of t. It's the first derivative of position. You take the derivative once. And then if you need acceleration, then you take the derivative again. So you can write it as a of t, or it's the first derivative of velocity, which is the same as the second derivative of position. So going this direction, from position to velocity to acceleration, you find the derivative. And remember, the process of finding the derivative, that's called differentiation. So you differentiate. But then remember, you can also reverse that process. You want to go from acceleration to velocity, velocity to position. To go this way, you can reverse differentiation and find the derivative, find the antiderivative or integral, and that process is called integration. So you can integrate to go the opposite direction. And then just remember, speed is a slightly different concept than velocity. They both have the same units on it, like feet per second or miles per hour, but speed, remember, can never be negative. So it's the absolute value of velocity. Whereas velocity can be negative because it indicates what direction something's going. Speed cannot be negative. And again, just think about on your car, it's called a speedometer, because no matter what direction you're going, there's no negative numbers on your speedometer. The lowest it ever gets is 0. That's true of speed. The lowest speed can never be a 0 if it's not moving. All right, so let's take a look at some example problems now. So here we've got a particle that's traveling along the y-axis, and so its position function, a lot of times they'll call it y of t. Just to remind you, it's moving on the y-axis, so up and down here. And time is in seconds here. And it says at what time, or times, so we're solving for the time here, is the particle at rest. So whenever you see that two-word phrase, at rest, remember that means it's not moving. And if it's not moving, what has to be true is that the velocity would have to be 0. So that's how we're going to solve this, figure out what times make the velocity 0. So for velocity, v of t, again we can write it either as v of t or y prime of t if you prefer, either way here. We would just take the first derivative, so that would give you 6t squared minus 42t plus 60. The derivative of 3 is 0, it's constant. And then just set that equal to 0. And notice you can factor out a 6 there. And you'll be left with t squared minus 7t plus 10. And then you can further factor that, factor the trinomial. Factors of 10 that have to be negative 7 would be negative 2 and negative 5. So 6 can never be equal to 0. So if you set t minus 2 equal to 0, you get t equals 2. And t minus 5 equals 0, t equals 5. And then remember, it tells you the units for time or seconds. So there's two different times, that's why it said time or times here in parentheses. At t equals 2 and t equals 5 seconds is when the particle is at rest. The significance of the particle being at rest, besides the fact that it's not moving, is usually the reason why it's at rest for just an instant is because that's usually when it's about to change direction. Not always, but usually that's when the velocity is about to change from positive to negative or from negative to positive. All right, then part B says the particle moving up. down or neither at t equals 1, a specific time. So again, what direction it's moving again involves the velocity. Here it's moving on the y-axis, so those are your possibilities, up, down, or neither. So moving up, that would be if the velocity is positive. Moving down would be if the velocity is negative. And neither would be if the velocity is 0, like we saw right here. So we already know it's not neither, because otherwise we would have found t equals 1 in part A as one of our answers for when it's at rest. So it's either up or down, so all you have to do is substitute in 1 into your velocity function, that one specific time. So v of 1, we already have velocity right here, is 6 times t squared, so 6 1 squared minus 42 times 1 plus 60. So the 1's make it pretty easy to calculate. That's just 66 minus 42 gives you 24. And the units here would just be units per second if we needed this. But notice that's not what it asked for. It didn't say what the velocity is. The key is that that 24 is greater than 0, right? That it's positive. So that tells us the particle is moving up. So we can change this question into a statement. We can say at t equals 1, the particle is moving up. And then it says give a reason for your answer, which is just another way of saying to justify it. So your reason would be since v of 1, which we just calculated, is greater than 0. We can say it's positive. All right. Take a look at the next part of this one. Part C says, what is the particle's average velocity over the interval 0 to 3? So remember, whenever you find the average of something over an interval, rather than what we found over here in part B, this was instantaneous velocity at one specific time. Here it's an average over the interval from 0 to 3. So remember, you start off with 1 over, in this case here's your A and B. So 1 over B minus A, 3 minus 0. And then remember, it's the integral on that same interval from 0 to 3 of whatever you're finding the average of, in this case velocity. So that just gives you 1/3. And when you integrate velocity, I mean, you could put the whole equation in here, but really, that just gives you back position, which in this case was y of t from 0 to 3. And so then we'll have 1/3, and it's just going to be y of 3 minus y of 0. So we just need to figure out what the position at 3 is and the position at 0. We get our answer. So y of 3, if we go back to our original equation here, would be 2 times 3 cubed minus 21 times 3 squared plus 60 times 3 and then plus 3. So let's simplify that here. So 3 cubed is 27 times 2 gives you 54. And then 3 squared is 9 times 21. Well, 9 times 20 is 180. 9 times 1 is 9, so 189. And then plus 180. 180 plus 3. So here, it's probably easiest to combine these that are close. This is 183 minus 189. That's negative 6, and 54 minus 6 gives you 48. So we go from right here, we'll have 1/3 and we just figured out y of 3 is 48. Minus y of 0, that one's a lot easier to calculate because 0, when you substitute in, wipes out everything but the 3. So minus 3. So that's 1/3 times 45. And 3 goes into 45 15 times. So you get 15. And for velocity here, it's just units for position since it's moving on the y-axis, and the units for time or second. So it's units. Every time you take the derivative, you divide by the units for the independent variable, which is oftentimes time. So 15 units per second is the average velocity on the interval from 0 to 3. All right, now let's take a look at part D, which asks about the average acceleration over the interval, same interval, 0 to 3. So the setup is similar because you're finding the average. It's still the same interval, 0 to 3, so it's 1/3 minus 0. Integral from 0 to 3. But this time what we're finding the average of is acceleration. So that's what we go here, a of t dt. So at first glance, you could find the acceleration function, put it actually in here, and then integrate it. That would work. However, remember when you integrate acceleration, you just get back velocity. Reversing that process from 0 to 3. So there's no need to actually find integration for this part anyway, for part D, because you just integrated using velocity. So here we'll have 1/3 times v of 3 minus v of 0. So we've just got to go back to our velocity function and find v of 3 and v of 0. So v of 3 remember was 6t squared minus 42 plus 60. So 6 times 3 squared minus 42 times 3 plus 60. So if we simplify that, that's 3 squared 9 times 6, 54, minus 3 times 40 is 120, 3 times 2 is 6, so 126, plus 60. So if we add up the positive numbers first, 50, 4, and 60 is 114, minus 126 is negative 12. So we've got 1/3 v of 3, we just figured out as negative 12. Minus, again, v of 0. It's a lot easier to just figure out in your head here. When you plug in 0, it wipes out everything but the 60 in your velocity function. So that's just going to be 60. So you have 1/3 times negative 12 minus 60 is negative 72. And 3 goes into 72 24 times, so that'd be negative 24. And then the units here, position was units, velocity units per second. So acceleration, the next derivative, would be units per second, which we usually write as units per second squared. Then part E on this one, it says find the speed of the particle. That's our end objective. But we have to find it when the acceleration equals 6. So when means, whenever you see when, that means you're solving for time. So we first need to find the time when the acceleration is 6. So let's find our acceleration function first, which you can write as a of t, or you could write it as v prime of t, the first derivative velocity, or you could write it in this case as y double time of t. However you prefer. Either way, or any of those ways that you might write it, you don't have to write all 3 ways, but you could, is you just take the derivative of velocity. So that would just be 12t minus 42. and then set that equal to 6. And solve it for the time, the wind part first. So if you add 42 to 6, you can see you get 48 equals 12t. And divide by 12 gives you t equals. So now we know the wind part. Now we know at 4 seconds, that's when the acceleration is 6. But now we need to find the speed at that time. And remember, speed is very similar to velocity. So let's find the velocity at that time. So by finding v of 4. So v of 4, remember our velocity function was 6t squared minus 42t plus 60. So 6 times 4 squared minus 42 times 4 plus 60. And if we simplify that, v of 4 is, let's see, 4 squared is 16 times 6 is 96. Minus 40 times 4 is 160. 2 times 4 is 8, so negative 168 plus 60. And again, if you combine your positive numbers first, you get 60 plus 96 is 156, minus 168 gives you negative 12. So that's velocity. Remember, speed is the absolute value of velocity. Speed can never be negative. So the speed then would be the absolute value of negative 12, which would be positive 1. But it still has the same units for velocity, which here are units per second. All right, let's take a look at a different problem here. This time it says the position's moving on the x-axis of the particle, and instead of calling it y-t, they call it x-t to remind you it's moving on the x-axis. And again, times in seconds. So it says determine the time or times when the instantaneous velocity, that's just our velocity function, v of t, that tells you the velocity at one instant time, equals the average velocity on the interval 0 to 3. Okay, so instantaneous velocity, we can just take the derivative of our position function there, v of t or x prime of t, if you prefer, is, we bring down the 3, that'd be, cancel out the 3's here, that'd be t squared minus 4t. So that's our instantaneous velocity. We want to know when does that equal the average velocity from 0 to 3. So we have to find the average velocity of that interval, so be 1 over 3 minus 0. The integral from 0 to 3. What we're finding the average of is velocity. So let's calculate what this is first, and then we'll be able to solve it. So we got 1/3. But again, we don't actually have to find velocity here because when you integrate it, I mean, you could put this t, we actually found it already on this side, but t squared minus 4t here, you could put that in there and actually integrate by hand. But it's probably a little easier to just remember that when you integrate velocity, you get back position. So that's just going to be x of t from 0 to 3. And then you can substitute those in. So you get x of 3 minus x of 0. And let's calculate what x of 3 is here off to the side here. So when you substitute in 3, you can see that would be 27 times a third, that's 9, minus 3 squared is 9 times 2, 18, gives you negative 9. So that's negative 9, and when you substitute in 0, wipes out everything, so that's just 0. So we have negative 9 times 1/3 gives you negative 3. So we're looking for when does that's our average velocity on the interval from 0 to 3. And we want to know when does this instantaneous velocity determine the time or time? When it equals that. Okay. So to solve this, you can just add the 3 over. So you get t squared minus 4t plus 3. And then see if it factors here. Factors of 3 that to be negative 4. It does factor, so that would be t minus 1 and t minus 3. Equals 0. So here there's 2 times. T equals 1 and t equals 3. And the units for time they tell you are seconds. So 1 second and at 3 seconds. There's 2 different times when those instants of time, the instantaneous velocity is negative 3, which is the same as our average velocity. All right, then part B on this one, similar question, except now it says when does the instantaneous acceleration, that's just another name for the second derivative of position, x double prime of t, or the first derivative of velocity, v prime of t, or we could just call it a of t. So we already found velocity was t squared minus 4t, so if we take the derivative of that, which is the second derivative of position, you get 2t minus 4. That's our instantaneous acceleration function. And we want to know when does that equal the average acceleration on the interval 0 to 3. So average acceleration, again, average is 1 over b minus a, 1 over 3 minus 0. Integral from 0 to 3 of whatever find the average of. In this case, it's velocity. Sorry, acceleration. So acceleration a of t. Again, you could put the acceleration function we have in here, 2t minus 4, and integrate it. Or you could just realize that when you integrate acceleration, you just get back velocity. And then that's just going to be evaluated from 0 to 3. So you have 1/3. And it's going to be v of 3 minus v of 0. And v of 3, if we look back at our velocity function from part A, which was t squared minus 4t, that'd be 3 squared is 9, minus 4 times 3 is 12. So 9 minus 12 gives you negative 3. So you got 1/3. v of 3 is negative 3. And v of 0, if you substitute in 0 into our velocity function, it wipes out everything. So that's just 0. So we have negative 3 times 1/3 is negative 1. So we're looking, that's our average acceleration on the interval 0 to 3 is negative 1. So we're looking to see when does this instantaneous acceleration, 2t minus 4, equal that. This one's a little easier to solve. You can just add over the 4 and get 2t equals 3. So t would equal 3/2. And equal 1.5 in units or seconds. In this case, there was just one time, whereas on part B, there were 2 different times, time 1 and time 3. All right, let's take a look at a different example here. This one says we've got 2 different particles that are both traveling on the x-axis. And the position of particle A is given by a of t. And the position of particle B is given by b of t. And what's the distance between the 2 particles at t equals 2? So let's first think about distance. It's kind of a similar concept in some ways to speed, because distance also can never be negative. It could be 0, but it's never negative. So just in general, if we knew what the positions of these particles were, to figure out how far apart they are, we should be able to just subtract their positions, right? So we should be able to find, at time 2, a of 2, its position, and subtract b of 2, its position, to see how far apart they are. only problem with that is what if a of 2 is less than b of 2? Then you get a negative answer, which wouldn't make sense for distance. So all you have to do to fix that, since distance is never negative, is just put absolute value signs around it. That way, whichever one you put first, the larger or smaller, the absolute value is always going to turn that difference into a positive answer. So that's all we have to find, a of 2 and b of 2. So a of 2, the position of particle A, would be negative 2 times the cosine. When you substitute 2 in there, it becomes 2 pi over 6, reduces to pi over 3. So negative 2 times cosine of pi over 3, if we draw that here. Pi over 3 is right here. Cosine is the adjacent of our hypotenuse, so the adjacent here, 1 over the hypotenuse 2. So that would be 1/2. And that gives you negative 1. So if we were to draw down the number line here, negative 1, that's where particle A is. Now let's find b of 2. So for b of 2, it's 3 times 2 times the sine of, when you plug in 2, that becomes 2 pi over 4 reduces to pi over 2. Pi over 2 is right here. And the sine is the y coordinate 1 right there. So that just becomes 6 times 1, which is 6. So on the number line here, 6, that would be where particle B is at. Now here, visually, it's easy to see how far apart they are, the distance between them. But you can see mathematically, a of 2 is negative 1, minus b of 2 is 6. So notice if we hadn't put the absolute value signs on them, that would give us negative 7, which doesn't make sense. You can see this, the distance between them is actually positive 7, right? So that's why the absolute value can resolve that. So instead of negative 7, which doesn't make sense for a distance, we got positive 7. And since it's just on the x-axis, it's just units. So that way, if you put the absolute value, it doesn't matter which one you end up putting first, A or B, the absolute value will ensure that either way it will end up being positive 7, or positive, the actual distance. All right, then for part B, it says at time 3, are the particles moving in the same direction or opposite directions? And then justify our answer. So to figure out which direction the particles are moving, we need to know their velocity. So you can write it one of two ways. For particle A, if you want, you can write it as a prime of t. Or if you want to remind yourself it's velocity, you can also use v and then just use a subscript, since we'll have two different velocities of particle A of t. Either way. And so when we take the root of that, notice we're just using the chain rule, so the negative 2 would stay on the outside. Root of cosine is negative sine of pi over 6t. So using the chain rule, you have to multiply by the root of a pi over 6 on the inside, which is, sorry, root of pi over 6t, which is pi over 6. And then you can simplify that. The negatives cancel out, and then 2 goes into 6 3 times, so you end up with pi over 3 times the sine of pi over 60. So that's our velocity, and now you can substitute in our specific time of 3. So we want to know which direction it's going. Is this moving left or right? Because it's moving on the x-axis. So this would be pi over 3 times the sine. When you substitute in 3, you get pi over 2, which is, we just figured out is 1. So it's pi over 3 times 1, which is pi over 3. And the significance of that is that it's greater than 0. It's positive, which means particle A at time 3 is moving to the right on the x-axis. Okay. Now for particle B, again, you can call it either b prime of t, or if you want to write yourself with velocity, v sub b of 3 of t. But this bird is a little more complicated because out in front it's not a constant, it's 3t. So notice we'll have to use overall the product rule there. They're multiplied together, both have variables, and instead of pi t over 4, we'll write kind of like we did here, so we don't have to use the quotient rule. That's the same as pi over 4t, like that. Okay. And so then when we take the derivative, using the product, the derivative of 3t is 3. Times the second one as it is, so times sine of pi over 4t. Plus the first one as it is, 3t, times the derivative of the second one. The derivative of sine is cosine, so it becomes cosine of pi over 4t, times, again using the chain rule, the derivative of the inside, the derivative of pi over 4t is just pi over 4. So on this one, you can simplify a little bit on the second term. There's not really that much to simplify. You can bring the pi over 4 out in front of the 3, but otherwise, you can just go ahead and substitute in either b prime of 3 or v sub b of 3, however you want to write it, would be 3 times the sine, and we plug in 3 here, it's 3 pi over 4. Plus, substitute 3 there, you get 9. And the cosine of 3 pi over 4. And then times pi over 4. So we need to find the sine and cosine of 3 pi over 4. So if we draw that over here real quick. 3 pi over 4 is in the second quadrant. And we're looking at the angle right here. That's the same as a 45-degree angle. This is 4 pi over 4. So the sides here are 1, 1, and root 2, but you can see this is the negative x direction. So sine would be 1 over root 2, which is the same as root 2 over 2. So we have 3 root 2 over 2. Plus 9 times cosine would be negative root 2 over 2. That's pi over 4. So, let's simplify the second term first here. So this will be negative, that's going to be 9 pi root 2 over 8. And to make it easier to get a common denominator, to see if it's positive, I'm going to get a common denominator multiplied by 4 over 4, so this becomes 8 on the denominator also. And that would give you 12 root 2. So, to see if this is positive or negative, you've got 12 root 2 minus 9 pi root 2. They're both over 8, so the question is what's bigger, 12 or 9 pi? Well, pi is about 3.14 times 9, that's going to be more than 27, that's much larger than 12, so overall this is going to be negative, so less than 0. Means this particle is moving left on the x-axis. So now we can answer the question. We can say at t equals 3, particles are moving in opposite directions, and then your justification would be since, well, we found v sub a of 3, or you could write it a prime of 3, that was greater than 0, and v sub b of 3, or you could write it as v prime of 3 is less than 0. Alright, so one more that just has multiple parts to it here. So it says the particle travels along the x-axis according to this position function. And the interval is just 0 to 3. So again, it's the x-axis position function, so we call it x of t. And we're just looking for from 0 to 3 where time is in seconds again. And at time 3 is the particle traveling to the left or right. Just correct. So again, what tells you if it's moving left or right is the velocity. So you could write it as x prime of t or v of t. Would just be 3t squared minus 10t plus 8. And then just substitute in 3 into that. So v of 3. 3 times 3 squared minus 10 times 3 plus 8. That would give you 3 squared 9 times 3, 27 minus 30 plus 8. So that's 35 minus 30 is 5. Again, the units here would be units per second. We needed those. But really all we're concerned with is whether it's positive and negative. In this case, it's greater than 0, which means it's moving to the right on the x-axis. So we can say at t equals 3, the particle is moving to the right. And your justification would be since v of 3 is greater than 0. Or if this was the y-axis, this would mean it was moving up, since we have a positive velocity. All right, then the next one, the way it's worded is might be a little bit tricky here. It says, when is the particle furthest to the right? So not moving right, but furthest to the right. Well, furthest to the right, that's always saying the maximum. And what the maximum is its position. So it's really asking you for the absolute maximum position. Or if it's, as we'll see on the furthest to the left one, which we'll do along with this one. Furthest to the left means the absolute minimum position. Okay. So the key concept to remember in calculus is whatever you're trying to maximize or minimize, you're eventually going to do both, is you need to use its derivative and find its critical numbers based on its derivative. So, since this is our position function, x of t, then we need its derivative, velocity, which we already found, remember, in part A, was 3t squared minus 10 plus 8, and set that equal to 0. And then you can factor that. So, factors of 24, 8 times 3, whose sum is negative 10. That would be negative 6 and negative 4. You can Use those to split up the middle term. So we've got 3t squared minus 6t minus 4t plus 8. And then you can split it in half and factor out the GCF. The first two terms is 3t. And then what's left is t minus 2. The GCF in the last two terms is negative 4. And you're left with t minus 2. Take out the negative 4 and then we're together to match up. So you can take out the t minus 2 as a GCF, and the other factor left is 3t minus 4. So you can see your critical numbers based on that. What makes this equal to 0 would be t equals 2 and t equals 4/3. So these are places where there might be an absolute min or an absolute max at those times. So to see where they are, then we have to draw a number line. And remember, we're just looking on the interval 0 to 3. So we draw a number line. We'll put brackets at the end. From 0 to 3. Notice 2 and 4/3 are both in this time interval. If we get any times here that we're not, those would be irrelevant, and we would cross them off. And here they both are. So 4/3 is 1 and 1/3, so it'd be right here, and then 2 over here. And then always label it, so this is v of t, our velocity. These are the two times that make the velocity 0, so in between those, they have to be positive or negative. So if we test here, you can see 0 minus 2, that'd be negative. 3 times 0 is 0 minus 4 is a negative. Negative times a negative is positive, so the velocity would be positive here. Between 4/3 and 2, probably the easiest thing, it would be like 5/3, because 2 is 6/3. So 5/3, that's less than 2, so minus 2 would be negative. And if you substitute 5/3 times 3, the 3's cancel out, you get 5 minus 4, which is positive. Negative times a positive is negative. And then if you test 3, 3 minus 2 is positive, 3 times 3 is 9 minus 4, that's positive. Positive times a positive is positive. So what this shows us is the position function x of t, which is what we're trying to maximize here. This velocity is derivative. You could put down this moving to the right, left, right. That would be correct. But it might be easier in this case to think about from the absolute maximum and absolute min, the position is increasing, moving to the right, decreasing, moving to the left, and then back to increasing. That way you can sketch a little graph right underneath here. So we know increase until 4/3, then decrease until 2, then increase until 3. Just a sketch so you can tell the maximum, absolute maximization. It could either be at this relative maximum at 4/3, or it could be at the end point of 3. Those are our two possibilities. So then to figure out which one it is, you just have to plug them in one at a time and figure out, well, what's x of 3 and what's x of 4/3, and see which one is larger. So x of 3, well, 3 cubed would be 27, minus 3 squared is 9 times 5, 45, plus 8 times 3 is 24, plus 1. Let's try adding up all the positive numbers first. So let's see, that's 27 plus 24 is 51, plus 1, 52, minus 45 is 7. So that's the position. It's at 7 on the x-axis at time 3. And then if you substitute in 4/3, this one takes a little more work here. 4/3 cubed, 4 cubed is 64, over 3 cubed is 27, minus 4/3 squared is 16 over 9 times 5. So, over 9. And 16 times 5, well, 10 times 5 is 50, 6 times 5 is 30. So 50 plus 30 gives you 80. And then plus 4/3 times 8, so that's going to be 32/3 plus 1. So let's get a common number. You can see that would be 27 here. So we can see if it's bigger or larger than 7. So we'll leave this as 64 over 27. Minus, we multiply by 3, that's 240 over 27. Plus, here you have to multiply by 9. So 9 times 30 is 270. 9 times 2 is 18. 270 and 18 gives you 288. Plus 1 is the same as 27 over 27. So that's going to give us, let's take these two that are close together first. 288 minus 240 is 48. 48 plus 64 is 112. 112 plus 27 is 139 over 27. And then let's see, does 27 go into 139 7 times or more? No, it doesn't. Because 20 doesn't even go to 139 7 times, so 27 definitely goes to 2. So this is smaller than 7. We're looking for the larger of the two, so in this case, 7 is what its position is. And then it says, when is the particle furthest to the right? So there's two components, and what is its position? So its position is 7. Okay, so you can say, different ways to word this, but one way to word it would be, turn this question into a statement here. The particle is furthest to the right. At the time was 3 seconds. T equals 3 seconds. And when its position is 7 minutes. That answers the second part of the question, what is its position? Okay, so that answers part B. And then part C, we're already set up to answer here because we already have the number line here. It shows us what the graph of position looks like. And now we're looking for the furthest to the left, which is another name for the absolute minimum position. So you can see based on our sketch here, there's two places that could occur. It could either occur at 0 or at 2. So we have to compare those two. This time though, we're looking for which one's smaller. So B of 0, sorry, not B of 0, X of 0, we'll know the position there. X of 0, that's going to wipe out everything but the 1, so you just get 1. And X of 2, let's see, 2 cubed is 8, minus 2 squared is 4 times 5, so minus 20. 2 times 8 is 16, plus 1. So if we have the positive ones first, that's 8 plus 16 is 24 plus 1, 25 minus 20 is 5. But this time we're looking for the lower of the two. Okay. So you can see 1 is less than 5, so that's our minimum position is 1 at time 0. So you can say in a similar way, the particle is furthest to the left at t equals 0 seconds, since, not since, if you did have to justify, it would be since x of 0 is less than x of 2. Or on the previous part, it would be since x of 3 is greater than x of 4/3, but it didn't ask to justify. You ask for what is the position, so you can say when its position is 1 Newton. All right, let's take a look at part D now. It's a little easier as we go now. For part D, we want the minimum velocity. It's a little clearer. That's talking about absolute minimum velocity. And part E, the maximum velocity. The time it reaches it and what is the maximum. So again, same key concept to remember. Whatever you're trying to minimize or maximize, you need its derivative. Remember here we were trying to find furthest to the right and furthest to the left, the absolute minimum and maximum position. So we had to use its derivative velocity and set that equal to 0. But now we're trying to find the absolute minimum and maximum of velocity. So we need velocity's derivative, which is acceleration, which I don't think we've needed to find yet. So acceleration, you can write as a of t, v prime of t, or in this case, x double prime of t. And if we take our velocity that we had right here, which was 3t squared minus 10t plus 8, take rid of that, would be 6t minus 10. And you set that equal to 0. Here you can either factor out a 2 and be left with 3t minus 5, or you can add the 10 and divide by 6. Either way, you end up with just one critical number of 5/3. So then we can draw our number line again. Again, we're just looking on the interval from 0 to 3, and 5/3 is in there. But this time, it's acceleration that's on our number line. And 5/3 makes the acceleration 0. So if we test 0 here, that's going to make this negative acceleration. If we test 3 or 2, that's going to be 9 minus 5 positive. So what this tells us is if the acceleration is negative, that's the derivative velocity. Now, it also does give the concavity, since it's a position, but that's not what we're interested in here. We're interested in what it tells us about velocity. The acceleration is the first derivative velocity, so velocity here would be decreasing, and then here would be increasing. So the sketch of it would look something like this, decreasing and increasing. So this time, it's easy to tell there's only one place the minimum could be of velocity. It'd have to be right at 5/3. So we know the time, but we also need to know what is the minimum velocity, right? So you also have to substitute in 5/3 in there into velocity. So let's figure out what v of 5/3 is. So if we go back to our velocity function here, it was 3 times t squared. So 3 times 5/3 squared minus 10 times t 5/3. And then plus 8. So if we simplify that, that's going to be 25 over 9, but then times the 3 gives you 25 over 3, minus 50/3, plus, we get a common number, 24/3. So you can see that's 49/3 minus 50/3 is negative 1/3. So that's the actual minimum velocity itself. So we can say, here this might be a little easier to work, you can say the minimum velocity is negative 1/3. Here it would be units per second since it's velocity. And it's just moving on the x-axis again. And then it asks for the time also, so at t equals 5/3 seconds. And then for the maximum velocity, if we go back to our picture here, we can see there's two possible places it could be. It could either be at 0 or at 3. So if you find v of 0, well, notice that's going to wipe out everything on our velocity function except for the 8. That would just be 8. And v of 3 would be 3, velocity function, times 3 squared minus 10 times 3 plus 8. So that's 3 squared is 9 times 3, 27, minus 30, plus 8. Gives you 35 minus 30, which is 5. But here we're looking for the maximum velocity. So the maximum is 8 in this case. So you can say the maximum velocity is 8 in units per second at t equals 0 seconds. All right, let's keep going with this concept here. It gets a little easier as we go. Parts F and G ask for the maximum acceleration and minimum acceleration. So again, key concept, remember to find maximum and minimum position, we need to use its derivative velocity. Then what we just did, to find the maximum or minimum velocity, we had to use its derivative acceleration. So if we want to maximize or minimize acceleration, we need the derivative of acceleration, a prime of t. And we know acceleration is 6t minus 10 from the previous part, so its derivative would just be 6. So notice if you try to set that equal to 0, it's never 0, which is okay. That just means we don't have any critical numbers. So when you draw your number line here, and then put on the endpoints of 0 to 3, and write down a prime of t. You can see a prime of t is just positive 6, so it's positive the whole way. Which means the acceleration a of t, since this is the derivative acceleration, is just increasing the whole way. And you can see that because notice the acceleration is just 6t minus 10, it's just a linear function. So it just looks something like that, increasing the whole way. And based on that, you can see, well, there's only one place the maximum acceleration could be. It has to be at 3. But we need to know what is the maximum acceleration. So we actually have to find a of 3. So remember, we know the acceleration function already was 16 minus 10. So that would be 6 times 3 minus 10. Gives you 18 minus 10, which is 8. So we can say the maximum acceleration is 8. And again here, it's acceleration, so the units per second squared. And that occurs, it asks for the time also, at what time does it occur? So at t equals 3 seconds. And then for the minimum acceleration, you can see that would have to be at this endpoint of 0, but you still need to find what is the minimum acceleration. So you find a of 0. So you just plug 0 into the position function. Sorry, the acceleration is 6 times 0 minus 10 gives you negative 10. So we know the minimum acceleration is negative 10 units per second squared. And that occurs at t equals 0 seconds. And finally on this problem, just a refresher on speed here. Speed, remember, is defined as the absolute value of velocity. It can never be negative. But oftentimes you're asked about speed being increasing or decreasing. And it's not quite as simple as velocity increasing or decreasing. If you want to know if velocity is increasing or decreasing, you just look at the acceleration, its derivative being positive or negative. If acceleration is positive, velocity is increasing. If acceleration is negative, velocity is decreasing. Speed is not quite so simple. You need to know both velocity and acceleration. So if the velocity and acceleration are the same sign, either both positive or both negative, that tells you speed's increasing. They're working in the same direction. However, if velocity and acceleration are opposite signs, if one's positive and one's negative, then they're working against each other, and that's going to cause the speed to decrease. So it says at t equals 1, is the speed of the particle increasing or decreasing? And then justify your answer. So we just need to find both the velocity and acceleration at time 1. So v of 1, we've already got our velocity function. Right here, remember, was 3t squared minus 10t plus 8. One squared minus 10 times 1 plus 8. Well, that just gives you 11. 3 plus 8 minus 10 is 1. So the importance of that is that it's positive greater than 0. That means the particle is moving to the right. But we also need to know the acceleration at time 1. A of 1, remember our acceleration function, was 16 minus 10. So 6 times 1 minus 10 gives you 6 minus 10, which is negative 4. And that's less than 0. So in this case, they're opposite signs. They're working against each other, so speed is decreasing. So we can say at t equals 1, the speed of the particle is decreasing. And then your justification, all you'd have to say is since we figured out v of 1 is greater than 0 and a of 1 is less than 0. Whereas if they were the same sign, both positive or both negative, then we would know that speed was increasing. And that concludes the notes for AP Calculus on the topic of position, velocity, and acceleration.